This lesson will enable us to tie up a few loose ends. The first thing we're going to do is to look at some specific types of nuclear reaction. Then we're going to describe the ionizing properties of the four main radioactive emissions. And then lastly, we're going to look at the random nature of these radioactive emissions, and we're going to look at the half-life exponential graphs of a radioactive element. Nuclear decay is when a nucleus is radioactive or gives off radioactive emissions naturally. Nuclear decay is spontaneous. Now, spontaneous is a very important term. It means that it will happen regardless of environmental conditions. It's random. Random is another defining word. But when we use the word random, we're referring to individual nuclei. You cannot predict when an individual atom will emit an emission. You can make generalizations about a large mass of a radioactive substance. You can say how long it's going to take for half of it to stop being radioactive. But you cannot predict the behavior of one atom. And so therefore, on an individual nuclear level, nuclear decay behavior is unpredictable, and it's uncontrollable because of this idea of spontaneity. You cannot affect the decay of radioactive nuclei by temperature, for instance, or pressure, or anything external. If it's decaying, it will decay, right? It will emit. There's nothing you can do to stop it. What you can do is capture those emissions so that they don't do anything dangerous. But generally speaking, you cannot change the path of a naturally decaying substance. This is an example of another type of nuclear reaction, which is fission. Now, this is very, very different to decay. Decay is when a nucleus emits alpha or beta or gamma naturally, right? Because its state is unstable. In this case, we are artificially making a nucleus unstable. We're inducing its radioactive behavior. And this is a very important reaction. We'll look at it in topic 8. It's called nuclear fission. It's when we force a nucleus to be unstable by making it too large and dabbling with that neutron-proton combination. And what happens in a nuclear reactor, for example, is that you bombard uranium nuclei, stable uranium nuclei. This is a stable isotope. You bombard it with neutrons until one is absorbed, and then thanks to that, the entire nucleus breaks apart and gives off 3 neutrons. Now, these 3 neutrons can then go off and make other uranium nuclei unstable and so forth. Again, we'll look at this in more detail in topic 8. But this idea of fission is when you take a large nucleus and you break it into 2. The nuclear equation, as you can see below, is balanced. And you can see here that the emission is actually a neutron. So you have a slightly different type of emission than the ones we've defined before. But anyway, this is what fission is, when you break a nucleus up. And as we can see here, this is a visualization, the absorption of the neutron by the nucleus. You have to control the speed of that neutron very carefully, and then you get 2 fission fragments and 3 neutrons. Okay, this is the next kind of reaction, which is called fusion. Fusion is another way to provoke a reaction which releases energy. I mean, the main purpose for a fission reaction, by the way, is to generate huge amounts of energy, and that's why we do it in nuclear reactors and bombs, etc. But fusion is very much sought after because this would provide clean energy. And fusion is when you bring small nuclei together to make larger nuclei. Now, the most common type of fusion reaction is hydrogen to helium, and this is what powers the sun. That reaction in the sun provides us with enough energy to sustain life on the Earth, for example. So we're considering, so that's huge, vast quantities of hydrogen fusing to make helium. And as we can see here, we get some fission fragments as well. We can express fusion using a nuclear equation, and as you can see here, we also get a balance of proton and nucleon number. And here we also get a released neutron, which is interesting. There's all kinds of combinations for nuclear reactions. Again, let's have a look at this last type of reaction, which is called an electron capture. Now, this is the opposite to what's happening with beta emission. When you destabilize a nucleon, you destabilize the nucleus by bombarding it with electrons. And what you're getting here is the opposite effect to that discussed before, where you get a proton absorbing an electron and making a neutron. Okay, and then that releases a neutrino. Now, the only reason I'm mentioning it is because I have seen it in an exam question before. But you would only be required to think about it in terms of an equation, really. I just wanted it to be familiar to you. Electron capture is one of the many, like thousands of types of nuclear reactor. But those are pretty much it. So the most common, I'd go back to decay, is naturally occurring radioactive emissions. And this happens in all naturally occurring radioactive material. And then you have fission and fusion. And I just thought I'd mention electron capture as an extra. Good time to note something called background radiation. Now, this is a very good example of naturally occurring decay reactions. And this is radioactive emissions from radioactive isotopes that occur naturally in almost all substances. So there are many types of rocks and minerals which contains traces of radioactive elements, and it's like basically tiny quantities, and they're constantly giving off background radiation. So you'll find that our bodies are actually attuned and very much capable of sustaining small quantities of radioactive emissions. And where do we tend to find them? Well, we can find them usually in minerals from rocks. Now, concrete is made from, partially made from rocks that are dug out locally. So if there are radioactive traces in the rocks in your local area, these usually end up in the concrete that's used in the buildings. So you do find that in basically pretty much every large structure. You do get them in medical sources, you get them in food, the air that you breathe, leaks from sources in power stations and hospitals. This would be relatively minor, we'd like to think. This is an interesting one. You do get a substantial amount of ionizing radiation that comes through space that's literally just flying around the universe, and it flies literally through the Earth. So it's moving through you right now. And then you have just basically soil and the Earth. So these are all sources of background radiation, and they're safe because you have evolved to be able to cope with certain amounts of radioactivity. Now, we're mentioning it here because we're going to look at half-life graphs and how to measure radioactive emissions, and this is a very important point. So what we're going to do now is look at how we measure the ionizing properties of these radioactive elements. The main piece of equipment that we use to look at radioactive levels is something called a GM tube, a Geiger-Müller tube, and a rate meter. And it's a neat piece of apparatus because what it does is it allows the ionizing particles to come in and basically move towards this filament. And as it joins this filament, it creates a circuit which allows a count. So you'll be able to hear on the video that I show you that there's like clicks. Each one of those clicks is an ionizing particle, which is creating a count. So obviously the more radioactive a source is, the more clicks you'll get, and so the greater the count. Now the units that are used, and we'll look at this in high level, are the becquerels, right, which are the counts per second. This is a measure of the quantity activity, and that's how we describe how radioactive something is, by looking at its activity. So let's see how we measure the ionizing properties of these particles.
Although nothing appears to be happening, all these substances are emitting nuclear radiation. It's invisible, but an easy way of detecting it is to use a Geiger-Müller tube attached to a counter. There are 3 different types of nuclear radiation: alpha, beta, and gamma. Each has a different penetrating power. So how does alpha radiation behave? This is an alpha source. At this distance, the count rate is about 500 per second. Place a thick sheet of paper in its path and all the alpha radiation is absorbed. Beta source. It emits only beta radiation. The count rate is over 600 per second. Place a piece of paper in its path and the count rate falls only slightly. Some of the beta radiation has stopped, but most travels through. Replace the paper with a denser material and the count rate drops much further. Beta radiation is absorbed by a thin aluminium sheet. Alpha, beta, and gamma. Each has a different penetrating power. Cesium-137 is a source of gamma radiation. At this distance, the count rate is about 50 per second. Place a piece of paper in its way and nothing happens. A thin sheet of aluminium also has no effect. Gamma radiation is very penetrating. Several pieces of lead are needed to absorb this high-energy radiation. Unlike
I apologise for that clumsy editing, but there you saw 3 experiments looking at the 3 different emissions, and it's quite interesting because there's a combination of factors at play. The first one is the mass. Helium has the largest mass, and so it's the easiest to stop, right? So the electrons, less so, because their mass is so much smaller. We're talking, if one electron is approximately 1,800 times smaller than a nucleon, we're talking about a considerable difference in mass. And so therefore you need something much denser to stop it. And then we have gamma rays, which are massless. And so it's very, very difficult to stop gamma rays. So we can consider the penetrating power in terms of the mass of the nuclei. But the other aspect we need to think about is how ionizing they are. Now, helium nuclei are highly ionizing. So if they do become absorbed by tissue, human tissue, for example, then they are extremely damaging because they cause more of an effect, more so than electrons or beta emissions, who have a charge of 1, right, which is half the charge of the helium nuclei. And then gamma rays are interesting because they don't directly ionize. What they do is if a gamma photon is absorbed by an electron, then that would cause an ionization of the electron. It's like kind of the difference between electrons being pushed out of the shell and an electron jumping, right, emitting, like jumping by itself out of a shell, which is less likely to happen, right? So on the one hand, this helium nucleus is way more ionizing and more dangerous. But on the other hand, gamma rays are much more penetrative. So it's more likely that you will absorb something like gamma ray because it's massless. This is something that comes up in tests occasionally, and that's what precautions to take, what safety precautions to take when you're doing experiments. So sources should always be kept in thick lead-lined containers to stop all kinds of emissions. You should use them for as short a time as possible. Sources need to be well labelled, obviously, in order to not mix up the different types of emission. You shouldn't touch sources of radioactive substances. You should handle them with tongs, and lead shielding should be used. And in fact, this is why when you go get an X-ray, which is a different kind of ionizing radiation, we're kind of mixing 2 things up, but for example, any kind of medical use of radioactive substances involves an awful lot of safety precautions, including lead shielding, lead-lined walls, etc., in order to stop that radiation spreading. The last thing I'll mention is how ionization takes place.